Okay, this is David, everybody. That's the best intro I can do.
Thank you. All right, so hi everyone. My name is David Wei, and I'm a software engineer at Meta. And today I'll be talking about some of the work that I've been doing with my colleague Pavel, who's not here. But yeah, I'll be talking about the work we're doing on zero-copy RX using IO uring. So I'll kind of start with the problem statement. The previous two talks have kind of already alluded to some of the things that I'm going to say. But basically, in production, we see a lot of bottlenecks that happen on the host, and we see these bottlenecks happen at the memory controller level, so bandwidth, system memory bandwidth to your main DRAM, and we also see bottlenecks that happen over the PCIe link with ML and AI workloads. So. Of course, you can't have a talk today without talking about ML, so that's kind of my token there. Of course, we also have overheads with doing these memory copies that happen in the kernel, and this is not like an old problem. This has been known kind of since the dawn of time. As NIC speeds get gradually faster and faster, we kind of see this overhead kicking, and that kind of limits to how fast we can actually move data. So how do you solve this? And the kind of classic way is, well, let's just get the kernel out of the way. Let's just bypass the kernel entirely. That kind of gives you, high throughput, low latency, or some mixture of both. But the obvious downside to this is not only do you have to re-architect your application to kind of support kernel bypass, you don't have a TCP stack anymore. You need to do all of this inside of user space. You also kind of need the rest of the system to also be re-architected. So all your standard libraries and services and whatnot that expects the kernel to provide networking capabilities, all of a sudden you can't use those anymore, and you have to kind of redesign the system around it. And that works for certain companies where performance at all costs makes sense. But for other companies, that's simply it's too expensive. You have to do it. You have to keep maintaining it, you have to keep feeding it and care for it, and that's not something we want to do. So then, what's the solution? Well, our proposal is to kind of have a hybrid solution where we essentially split the stack into two, and we have a standard control plane stack, so the kernel is going to process all of your headers, your TCP/IP headers and whatnot, and we're going to introduce this fast zero-copy receive data plane, essentially, and we're going to do this using IO uring. And yeah, there's a diagram, and I'll go into each part of that in the next section. But before that, just a quick primer on IO uring for those of you who might not be familiar with what it does. So IO uring is a way to do fast asynchronous IO, and with far fewer system calls. So traditionally, when you want to do like a send or a receive, these are all system calls. You provide the buffer that you want to receive data into, then you make a system call, and that enters the kernel, which then does the work for you. So IO uring gets around this by introducing two ring buffers that are shared between the kernel and user space. The first one is the submission queue, and the second one is the completion queue. So essentially, user space submits their work into the submission queue, and this can be done. And this is one of the advantages of doing it like this, is that you can actually batch your work in batches, I guess. And then once you've prepared your work, you then enter the kernel. The kernel then handles the request that you've submitted. And then for each request, the kernel is going to post a completion event into the completion queue. And then that's going to return back into user space, who will then read the completion queue, and then, does whatever it needs to be, probably repeat this cycle, right? Like submit more work, complete more work, and so on. So yeah, the first step is to kind of prepare a request, and to do this, you get a submission queue entry or an SQE, and then there's a bunch of helper functions in lib uring that kind of prepares the request. What type of request is it? In this case, it's a receive request. You pass in the socket you want to read the data from. You pass in some buffer length flags, all the usual stuff. And note that when you get the request, when you get the SQE, that already kind of moves the tail of the submission queue. So you do this a couple of times, you kind of prepare your work, and then the next step is to enter the kernel. And you do this with, there's different ways of doing it, but typically the way you would do it, the preferred way of doing it today is you do this submit and wait. And what this means is you say, okay, well, submit everything in the SQE, and then I'm going to wait for a certain number of completions before kernel returns back into user space. And then once the kernel is done with the work and then the number of completions has reached the amount that you specified, the control returns back into user space, and then user space is then free to process the completion events in order. And you can do this with this for each CQE loop. And then once user space is done, it needs to actually move the head of the completion queue so that the kernel can see that, okay, you finished consuming these entries and I'm free to reuse. I'm now free to reuse those entries. Cool. All right. So next we'll talk about the kind of proposal or the design of our proposal. The first step is we need to actually register the user space memory with the kernel. And we do this with IO uring. IO uring already provides this functionality. It's called registered buffers. And essentially what this does is it takes some user space memory. It's going to then pin it and then chunk it up into pages. And what we essentially end up with is this array of struct biovex in IO uring. All right. So the next step is we need to actually get these pages into a hardware RX queue. And we do this by adding a new page pool that's heavily inspired by the existing page pool. So the only kind of real difference is that this page pool is going to be backed by the user space memory that's been registered and now owned by IO uring and pinned, as opposed to being backed by kernel pages. And in order to tell the driver, which queue should actually use this page pool, we added a XTP or we added like an NDO command that then says, for this specific RX queue, I want to configure it for 0 copy. So when you fill that RX queue with pages, please use it. Please take them from our 0 copy page pool. Otherwise, use the standard page pool. And then to kind of manage this, we added a very thin shim layer that basically does that check. If RxQ ID is configured for 0 copy, then use the 0 copy page pool. Otherwise, use the standard page pool. So the end result of this kind of setup stage is that you're going to have these Rx hardware queues that are basically filled with pages that come from user space as opposed to kernel space. And as Mina mentioned earlier, like the hardware, the drivers, they don't really care what the pages are. They just look at the DMA address, and then when packets come in, these the packets just get DMA to wherever it's specified. And so what's going to happen when data comes in is that they will be DMA'd into its final destination, intended destination in user space memory. Cool. So we also depend on some hardware features in the NICs, namely header splitting and flow steering. So we ideally only want the payload to end up in user space. We don't want to give user space the headers. Or if we do, then we certainly want to take a copy of it in the kernel, because we're not going to, we're not going to trust user space to not kind of trash over the headers. So ideally, we have header splitting. In this case, each Rx queue are actually backed by 2 different queues, one for the headers and one for the payloads. And I think that was a question earlier, right? Like, what do you do in that case? So we only fill the payload RxQs with user space pages. The header RxQs are still going to be backed by kernel memory. And of course, in modern hardware, we typically have a large number of RxQs, and we only want flows that belong to the application that we are optimizing for to end up in those queues that we've carefully configured for zero copy. So to kind of stop other flows from entering and to only make sure the flows we want enter, we use a combination of flow steering to get the flows we want into the RxQs, and then we use RSS rules to stop the other flows from being hashed into our zero copy RxQ. Cool. So once the hardware side is set up, as packets come in, it's the usual goodness that we know and love. So packets come in, they get DMA'd, the device notifies the kernel via IRQs, and then the kernel is going to run soft IRQs to kind of nappy poll the queues. It's going to construct SK buffs, and then these SK buffs will make their way up the stack, eventually ending up in a socket. And just like what Mina talked about earlier, we also mark these SK buffs with a special flag because there are bits of the networking stack that might do copies or manipulate or touch the pages, and we don't really want them to do that. So we mark it with this special flag to make sure that it's not going to touch it, it's not going to copy it, and it's just going to kind of leave it alone. Cool. So now, how do we actually get the data in user space? And this is kind of like the control plane that I was talking about. So we use our uring for this, and the first thing is we add like a new request type to IO uring. It's called a zero copy receive request. So user space will prepare a submission queue entry and submit it into IO uring. And what this request is going to do in the kernel is that it's going to just read from the socket. So the request is going to read the socket for SKBs, and then these SKBs are marked as zero copy. We also tag the user space pages that we registered for zero copy with a special cookie that kind of tells us, okay, this is a zero copy page, and to handle the request, we don't need to do any copies here, right? The data is already in user space, already been DMA'd there. So really, this is more of a notification mechanism to tell user space, hey, go look here for the data that you actually want. So to do this, we added two new shared ring buffers to IO uring, and one of them is highlighted here. It's the zero copy RxQ, and then each entry in this queue, I have the structure there. So each entry basically has the offset length relative to the user space memory region that was originally registered, and then eventually user space will read this, and then that will tell user space, okay, the packet data that I'm looking for is in this location. Oh, and there'll be one of these entries for each page frag, for each zero copy page frag in an SKB. Cool. So once our uring has processed the packets in the socket, whether we exhausted everything in the socket, or we ran out of space in that zero copy RxQ, or we hit some kind of read limit, we kind of return control back into user space by posting a single completion into the main completion queue of IO uring. So now with control back into user space, it's going to look at the completion queue entry, and it's going to tell the application to, okay, I need to now go look inside of this zero copy RxQ, and then I'm going to read each entry. And each entry says, your packet data has this offset, has this length, inside of this region. So the application can then go and find its data there. After that, the application will use the data, do whatever it wants with it, and then once it's done, it needs to actually return this data back into the kernel, and such that it can be refilled, such that the hardware RxQ can be refilled. And this is done by using that second new ring buffer that we added, and this is called the refill ring. So each refill and entry is again an offset in length. And the user space will write entries into it. And when control goes back into the kernel and we're refilling the hardware RxQs, the zero copy page pool is going to use entries from this refill ring. Cool. So I'll share some early preliminary results that we got. So these experiments were measuring the memory, the system memory bandwidth, and this was done on a system with 62 gigs of RAM. We had a Broadcom 57504 NIC, and we used iPerf3, a modified version of iPerf3 to kind of use the new uring API. And I'll show results for both an AMD and an Intel system. And all of these numbers were measured using like vendor-provided software. So for AMD, we used uprof to measure this. And for Intel, we used PCM. So so for the AMD system, we see the difference between zero copy and non-zero copy. There is a significant reduction in the overall system memory bandwidth. And these are the results for an Intel system. So one thing that kind of is different about Intel, I think I mentioned it in one of the questions from yesterday. Intel had this thing called DDIO, and it kind of messes with the results, especially with iPerf, because iPerf doesn't do anything with the data, it just throws it on the ground. So for this experiment, I had to explicitly disable DDIO on the system. Okay. Cool. Any questions?
Hi. So you have not mentioned how is the allocation being made regarding the physicality of the pages. So are you using Hue pages here? Also, are you using Jumbo frames? And if so, which size?
So we are not using huge pages, and we're using standard, I guess, 1500 MSS. So that's one of the things about our proposal, is that we are not, we have fewer limitations on things like requiring jumbo frames, because doing it through uring is very efficient. So yeah, we don't have the same kind of restrictions. And for for huge pages, that's something we want to look into, but we haven't done it yet. Okay.
Thank you.
So you mentioned the buffer register thing with uring.
Yes.
There's two ways to do that: the register buffers and the register buffer ring thing. Does it work with both, or?
I would say that this is a third mechanism for registering. With
okay. So you're adding a new register for zero copy.
That's right. Yeah, because we're adding these two new ring buffers. So the registration process is tied to the creation of these two new ring buffers that we're adding to uring. Yeah.
Okay. And other question, is this going to work for receive message with the extra control data?
Probably, but I don't know yet.
Okay, thanks.
Mm-hmm.
Well, uring bypasses receive message, right? You're giving the message to user space through the completion ring, through the new Rx ring.
Yes.
Yeah, but you still need the C message data if you, for example, need the incoming address for a UDP packet.
It's going to be in that receive message, the new Rx ring CQE. Right, so you don't have to call receive. The whole point of uring is avoid system calls.
Yeah, but you still need the data.
Is the data in the header? Is that what you're saying?
Yes.
Okay.
So there are special mechanisms to handle this for receive message. If you use a buffer ring, it takes the first part of the buffer and reserves that for all kind of C message, like whatever. But that would be in the zero copy buffer in your setup, so that's why I'm asking.
Okay. Yeah, we'll have to look into that, yeah.
David, hi.
Hi.
There does seem to be a lot of overlap between the two talks, right?
It does, yes.
And actually, they're complementary because whether you use the receive message or IOU ring, potentially IOU ring is just much faster. Do you think you could use the same memory provider backend for this?
Yeah, that's a really good question. So for our design so far, we kind of created this parallel page pool, zero copy page pool. But yeah, once the memory provider backends for page pool gets added, we will definitely move our solution to use it because it's a much neater way of solving the problem, right? There's fewer duplication in the networking code then, and we can just be one of the other. We can just be another memory provider for page pool. So we're going to end up with three, is how I'm imagining it, right? You have the standard kernel memory, and then you have the user space memory that we're adding, and then we're going to have device memory, which is the work that Mina and you are working on.
Yeah, I hope so. And actually,
Yeah.
the Mina demonstrated the SODEV mem, we call it SODEV mem, but with the US DMA provider, with the user space provider. So I think there is overlap there.
For sure, yeah.
Thanks.
And yeah, and one of the future work for us is to obviously move this from host memory to also device memory. And we were going to do that ourselves, but thanks to and you at Google doing this, we'll look at using the great work that you're also doing. Hi. Oh, I think the microphone is not working.
Here you go. Here's another one.
Hey, David, thanks for the talk. What's the status of this for their patches?
Yes. So the first version of our patches is on the mailing list, and that was sent back in August. And you can expect more patches more frequently from now going forwards on the mailing list. So yeah, if you're interested, please take a look. Please comment. And to add, one of the things we're doing in the second version of the patch set is we're going to add a very hacky VF-based solution, such that you can kind of play with the uring bits and pieces without depending on like a very specific Broadcom NIC. And without depending on some out-of-tree patches that you would need to kind of add flow steering to those Broadcom NICs. So yeah, we're working on that, and yeah, please expect to see patches soon.
Okay, that will be great. Thanks.
Yeah.
Yeah. So it sounds we already need infrastructure for this header data split with multiple page pools for the drivers. I mean, not initially, but was there any discussion about this, both on your side and on the Google side?
I'm sorry, go ahead.
So is your question the kind of requirements, the hardware feature requirements we need, header splitting?
So on one hand,
necessary.
yeah, it's necessary. That's clear.
Yeah.
But also for the drivers to have this support for the different, so page pool with different memory providers.
Yes.
And you need some kind of idea to link this to, because the header data split and zero copy seems like a good, maybe a good point to introduce this under, so that not every driver implements it so differently.
So
right.
I don't think you need a page pool for the headers, because the headers essentially go in the SKB linear, and it's only small, so you can just you don't need to allocate page frags for this, right? And what we actually do, or suggest devices do, is you only need as many header buffers in the device as there are elements in the receive queue. So pre-allocate a contiguous piece of memory and DMA map that once as consistent memory to minimize the IOTLB entries. And then when the packet comes in, copy the headers into the SKB linear, because you need to prime the cache anyway.
All right, got it.
Yeah. And for what it's worth, header splitting, it's a nice to have, but it's not a requirement for this to work, right? You can imagine situations where we can DMA the whole thing into user space, but the kernel takes an authoritative copy of the headers, and we only work with that authoritative copy, right? So then user space can trash the headers however it likes, and it's not going to affect the rest of the networking stack.
Okay, thank you.
One quick question: is there any chance of what I would call leakage, where you've got a receive queue and a packet that's really not meant for this shows up. And maybe the kernel has to look at it and decide, no, I won't give it to you. I won't notify that it was completed. I need to do a, backdoor copy to something else and recover.
Yes, I do have a slide, but my computer's not working. What's going on?
This is a random question. Is anybody looking at improving NAPI? Okay.
Sorry, to first answer your question, we have a scheme called a copy fallback, and I don't know why I have a slide for this. I don't know why it's not working, but we have a mechanism called copying fallback, and it's for situations where, as you describe, where you might have a stray packet that end up in our zero copy queue that shouldn't really be there. It also, when hardware header splitting fails, if you split too much or too little, this copy fallback mechanism makes sure that things kind of work or degrade gracefully. And the copy fallback is also important for, I guess this applies to any kind of zero copy or mechanism where you have to register something ahead of time, right? Like RX traffic is very bursty. The application needs to know, how much should I allocate? Too much and you're wasting memory, and too little and you end up exhausting it. So the copy fallback is a mechanism that we have to kind of support these cases. So if it gets triggered because the user-space memory gets exhausted, the system kind of kicks out of the zero copy mode. And then we give user space and notification to say, hey, by the way, we've left zero copy mode, and because your buffers were exhausted. So that gives user space an opportunity to okay, let me allocate more, let me double the size or something, right? And then once it's happy, it can then kick the system back in. So we have a mechanism for this. And yeah, it'll be in the second version of our patch set. Cool.
Okay, so there is an online question. William, do you want to come on stage, or you just want me to read it?
Okay, so the question is, the design looks very similar to AFXDP with UMEM. Any reason for not using AFXDP or XSK socket? So I don't know too much about AFXDP. I'm sorry, there's a lot of things I don't know. My understanding for AFXDP is that we pass the whole thing into user space, right? And we don't process the headers. Is that right? Right, it's like a form of bypass. So, like I was saying earlier, that won't work for our services. That we want the kernel to still process the headers. Cool.
Okay, let's give it up for David. Thank you.
Thank you.
Oh, and before you leave,